So we know that confounders, stuff that happened before the exposure and that could potentially affect both the exposure and the potential outcomes, we know that those contribute to bias if we leave them out, because then if we don't have them, then we don't get that conditional randomization satisfied, and then we don't have the identification. So you can get bias if you don't adjust for them. So we want to kind of include all the things that we measure. We ideally want to measure all of these unobserved things as well. We don't want to leave anything unobserved, basically. So we're going to try to collect as many of these confounders as possible. And again, you cannot test whether something is a confounder or not, because the conditional independence that you need to test is between the exposure and the potential outcome. But you don't get to see the potential outcome, you get to see the observed outcome. And so with the data that you have, there's really no way to say whether what the kind of DAG looks like. So this has been known for a long time, and it's been known for a long time so much that people are writing papers repeatedly, year after year, saying, stop doing this, stop trying to test for confounding. But it is subtle, right? And so, if you want to dig into it, you can read this paper and others to understand this a bit better. But so you can't test what's a confounder. You have to think about it using your domain knowledge. You have to understand what might impact both the outcome and the exposure. However, just because something is a confounder or something is before the exposure, it doesn't mean that they all totally behave the same way. So let's think about some extreme cases. So what about variables, things that happen before the exposure that affect only the exposure? Or there's variables that affect only the outcome. So for example, let's say if you were trying to study whether or not somebody votes in an election, and then their downstream political engagement in a couple of years, like whether they're volunteering for campaigns or something like that. If you had somebody who kind of came and knocked on your door and encouraged you to vote, or had you fill out a voter registration form, that might be like this variable I, because they're just encouraging you to vote. They're not directly impacting your involvement in the campaign. You're never going to see them again. But maybe the fact that they encouraged you to vote is what led you to decide to kind of work on a campaign in the future. But it wasn't direct. It only affected that outcome through this exposure. Another thing is this other kind of variable that I have written as here is E, which is only affecting your willingness to work on a campaign. So maybe this is like the attractiveness of a particular candidate. It didn't make you vote in this election, but that did contribute to your willingness to work on their campaign later on. That's an example. There's many, many more. So these variables I'm going to call I an instrument and E an explainer. And so here's an example data generating process that is like reflective of this DAG, where the exposure is determined based on the value of X, this confounder, and then also the value of this instrument. Whereas the potential outcome is determined based on just the explainer and the confounder, but not the instrument. Why are they called instrument and explainer? Well, the instrument, this is also called an instrumental variable. It's something that, like I said, only affects the exposure. It can affect the outcome, but only through the exposure. We'll talk about it in a sec. It's called this. It's an old term, but basically, instrumental is in the sense of it being necessary or useful. And there's this whole thing called instrumental variables analysis, which kind of tries to get around the no one observed confounding assumption. I think we did have this in a challenge assignment. But in other words, instrumental just means like important or useful, and it comes from this kind of the econometrics literature in the 40s or 30s. But for whatever reason, that name stuck. Now this thing, explainer, I made that up. So you may see this called a prognostic variable or explainer, and it's just something that just explains the way variability in the outcome. We'll see a bit more about that later, but it doesn't affect what somebody's exposure was. And I actually asked ChatGPT what a proper name for this should be, right? And because I said, there's no set term for the opposite, right? So I asked ChatGPT to coin a term, and it said outstrument, which I love. I don't think it's great, but I just think it's so damn creative because, this thing is called an instrument, and instead this thing just called an outstrument because why? It affects the outcome, and then it mirrors the use of instrument. I was just like, wow, that was the point where I thought, okay, this generative AI thing, there's really something to this. Like, I don't care that I can write good code or whatever, like, fine. But this, like, that's a gem. Okay, so the question is, these things aren't confounders, right? Technically, they're not confounders because they don't affect both exposure and outcome. They only affect one or the other. So do I need to adjust for them? And note, however, the instrument, like I said, does affect the outcome. The instruments do affect the outcome, but not directly. It only affects the outcome in a way that is mediated through the choice of treatment. So effectively, if I know that somebody took the drug, I don't care. It does not matter if they were encouraged to take the drug or not. That doesn't tell me anything more about whether they got healthy or didn't. All that matters is whether they took the drug. So instruments are fully mediated through the choice of exposure. So they're not confounders, neither are explainers. If I include them in this, as long as I'm conditioning on X, if I also condition on I and E, it doesn't matter. I still get this conditional independence. So I still get the identification. So there's no bias. So I can include them in my regression model, right? That doesn't induce any bias, no problem. The question is, what about variance? Because this just gives me identification, but it doesn't tell me anything about then statistically how closely can I estimate this thing using the data, right? So let's figure this out. Let's do a little simulation. I'm going to set up a data join process with an explainer, an instrument, an exposure. So notice the exposure is affected by the instrument, and then the outcome, which is affected by the explainer. And here, the effective treatment is 0. So I don't have any treatment term in the outcome, but I don't know that a priori, right? That's just baked into the data join process, but I'm going to pretend I didn't know that. And let's fit some linear regression, draw out some data, fit linear regressions, including neither of those, instrument explainer, just the instrument, just the explainer. Estimate the causal effect using the marginal effects package and the robust standard error, and then look at the results. So here we go. These are the 3 different models. This is the estimates and the standard errors. So just by looking at the standard error, it looks like our model is way more confident about the causal effect when I include the explainer. Less so when I just have the treatment. And it's actually the least confident when I've added the instrument. So you may think, okay, well, is it just that these standard errors are being somehow messed up by the inclusion of these terms? But they're not, because these are the robust standard errors. We didn't do any model selection or anything like that. So these are accurate. Now let's look at the estimate, right? Because of this variance, which is reflective of some real sampling variability, we can see that the estimate is actually very far from the truth when I include the instrument, and it gets closer. The truth is 0. It gets closer when I include the explainer. So I can repeat this 1,000 times and plot actually the true sampling distribution of the ATE in each case. And what we see is that including the explainer really helps in terms of estimating the effect of the treatment. Leaving it out, okay, not so great, but including the instrument actually hurts us if you compare these 2 distributions. This one is a little bit more peaked, and this one is a bit more spread out. It has fatter tails. So in general, we're getting bigger estimation errors when we include the instrument, smaller when we include the explainer. And this is purely an impact on variance. They're all unbiased, right? Even though this is more spread out, we're getting larger errors in general. On average, our error is still 0 because this thing is centered here at 0, which is the right answer. So all of these are unbiased. Up to, these don't look perfectly symmetrical, but that's just because I only ran this 1,000 times. So it's really just an impact on variance, which aligns with the theory here, right? That we know that this identification result should hold, so everything should be good. Assuming the model is correctly specified, but in this case it is. We have a linear, the truth is linear. So why does this happen? Well, explainers explain away variability in the outcome. So let's say you're just comparing your outcome measurement between these two groups, the exposed and the unexposed. If you just look at this, like with the naked eye, it's maybe you can see that the exposed are doing a little bit better on average, but it may just be noise, right? Like it could just be this, if you just move this one person down here, the answer could be different. And so there's a lot of uncertainty if you're just looking at this. However, if you spread these people out along an x-axis here, where this is the explainer, and you look at the data like this, you can see very clearly that for each stratum of the explainer, there's a clear difference, right, in the outcomes, and that makes it very obvious that there is a causal effect from the treatment. So effectively, what's happening is that this variability in the explainer is explaining away the variability in the outcome, which is precisely why I like to call this thing an explainer, because that's what it's doing. It's explaining away some variability, and that means that the effect you get, there's less uncertainty in that treatment effect estimate. You're going to get smaller standard errors in general. What about instruments? Instruments, they are collinear with the exposure. So we actually already saw a picture like this, I think, last week. And we saw that when two variables are collinear, the coefficient estimates for each of them are going to have really big standard errors, because it's really hard to tell what the coefficients should be, because you can kind of rotate this plane and change the coefficients, take a little bit away from I, put it into A. And that what that does is that it rotates this regression plane. And it's, these all fit pretty much equally well. And so that's just going to induce a large standard error on the coefficient for A, which kind of no matter which way you slice it, when you translate that variability and that coefficient into the variability on the ATE, when you calculate the marginal effect or the plug-in estimator, that's going to translate over there. So, bottom line is, okay, adjusting for pure instruments, bad. They're going to increase your variance relative to if you hadn't done that. Adjusting for explainers, great. Going to decrease your variance. But in reality, these things are like unicorns, right? It's really hard to find a thing that's purely an instrument that is not, there's no plausible way where that this thing could have directly affected the outcome, and there's no plausible way that this thing could have directly affected your treatment. Like the example that I gave where this is somebody knocks at your door and encourages you to vote. Why wouldn't that, even if you decide not to vote, right? Why wouldn't you think about that a couple months later and say, hey, maybe that person had a point. It's important to vote. And then you look up somebody's campaign and you decide to get involved, right? So that could have had a direct effect. It's totally plausible. So generally, these instruments and explainers, they really do have some small effect on the exposure for an explainer and on the outcome for an instrument. So maybe the data generating process looks more like this, where you have the explainer coming into the exposure, but it's just a small effect. Like the coefficient here is 0.1, whereas the coefficient for the instrument is 10, and vice versa for the outcome. You have a kind of a smaller impact from the instrument and a larger impact for the explainer. So what about in that case? The real question is, should we should we adjust for something that we think is a near instrument that more affects the treatment than the outcome? Because we know that if it's a pure instrument, that's going to be bad because it's going to inflate variance. But this thing technically, since it affects the outcome, it's technically also a confounder. So if we don't adjust for it, that breaks our identification result, and there's going to be bias. So it's kind of like we're damned if we do, we're damned if we don't. So what should we do? So here's a very simple simulation. Here I just have the instrument and the exposure. There's no explainer to worry about. The instrument is affecting the choice of exposure in a very important way. It's not really affecting the outcome too much, only a little bit. Okay, and I'm running two regression models. So this is what we call a near instrument. In the two regression models, I'm saying if I ignore the instrument or I adjust for it. So we know that this one might have a little bit of bias because I'm basically not including a confounder. However, this one might be inflating the variance. So which one is worse? And here's the results. So in this simulation, we can see actually that yes, there is a little bit of inflation in the variance. If you compare this to this one's a little bit more spread out. But the bias here is pretty substantial, and there's really no bias here. And that's what we expected to see. But in general, and then this is a pretty extreme case where this instrument has just a little effect on the outcome, and so it's almost a perfect instrument. But I mean, I think that the decrease in bias generally makes up for the increase in variance. It really depends on what you're studying, right? Like if you really, really want to make sure that your result is not biased at all, and you want to have perfect, type 1 error control, and maybe you're doing something for regulatory purposes, then it's probably most important to reduce the bias, and you don't care about the variance. You're just going to eat that. But in other cases, maybe it's worthwhile thinking about. Maybe I shouldn't include this, but overall, I would say that these things are quite rare. Pure instruments, generally things are affecting the outcome as well. So unless you have a really good reason to say, I think there's no plausible way in my mind where this variable could affect the outcome besides through the choice of exposure, it's generally safer to include it as an adjustment variable because of the confounding effect, and you want to reduce that bias. So overall, this is the picture. We have here, for confounders that are more like instruments, yeah, they inflate the variance a bit. For confounders that are more like explainers, they're going to reduce the variance. You definitely want to include those. And for all of these, you're going to reduce the bias to some extent. And the bias is reduced. The amount of bias that you're reducing is basically related to how strong of an effect these things have on both of these. So if you have a confounder that strongly affects both the exposure and the outcome, that's going to reduce the bias a lot if you adjust for it. If you have a variable that basically does nothing for both of these, you adjust for it, it's not really going to reduce the bias that much. Corollary, interesting corollary. In a randomized trial, everything is an explainer. Everything is an explainer. Why? Because in a randomized trial, you randomize the exposure, so nothing affects the exposure. You've cut off all those arrows, so there are no confounders. Nothing is a confounder. Nothing can be an instrument. Everything is an explainer. You just have strong explainers and weak explainers, right? And the strong explainers are going to give you a large variance reduction. The weak explainers, will still reduce the variance maybe a little bit, asymptotically if you include them, but not a lot. And none of these is going to affect the bias at all because it's already zero. You have no confounding, so you can add in basically whatever you want as long as it's pre-treatment, okay? And I want to emphasize this because it's astounding. People don't adjust in randomized trials because they think, well, I don't have to adjust. I can just take the naive ATE and the effect is already identified. And they're not even thinking like that, right? Like they don't understand what identification is. They just think, okay, randomized trial, I just take the difference in group means, call it a day. Okay, yeah, you don't have to adjust. You're going to get an unbiased estimate, but why would you take this sampling distribution when you could have this sampling distribution? Why would you have this standard error when you could have this standard error, right? And it's so common that people just use unadjusted estimates in randomized trials that the FDA has to say, please, for the love of God, adjust in your randomized trials. So they put this out a couple of years ago. It's super recent. I mean, people have been doing randomized trials for decades, like almost centuries, right? People have been doing linear regression for basically a century, and still, I mean, it's embarrassing. So they say here that, yeah, you have to identify covariates that have an important influence on the primary outcome variable. So that's explainers. You have to, of course, pre-specify the analysis. You cannot do model selection unless you do data splitting. And you should not adjust for anything measured after randomization because that could be a collider. So exactly what we've been talking about. And it says, why do we do this? Well, adjustment for prognostic baseline covariates leads to improvements in precision because it reduces the residual variance. Here, there's also some additional considerations for nonlinear models. We'll talk about that next week and the week after. But basically, it is the same idea. It's just that if you're doing the marginal effect, the kind of plug-in philosophy, everything works the same way. If you're doing the thing that people generally do and look at these coefficients, that becomes more complicated and it's silly. But you shouldn't be doing it in the first place. So just everything transfers over quite nicely. Yeah, conclusion for this section is that when you're doing causal inference, the variable selection has to be based primarily on domain knowledge, not statistics. So this DAG, you cannot decide on what goes where by looking at your data. You have to think. You have to read papers. You have to talk with people who understand the domain, what order things happen in, what likely relationships between variables, and think about this kind of stuff and what happens before, what happens after. If it's after, don't adjust for it. If it's before, you can at least consider, maybe how your results would change for different variables. Maybe think about instruments, but generally everything before is kind of fair game. So let's practice. Say you're working on a study. You want to understand how adverse childhood experiences, let's say in elementary school, affect higher educational attainment. So years of school completed. So like high school versus college versus grad school. And you run an adjusted analysis. You control for socioeconomic status, let's say of the parents at birth. And you also do an unadjusted analysis. In your unadjusted analysis, you see a significant result. It shows that having an adverse childhood experience lowers educational attainment by about a year, plus or minus 6 months. So it's pretty significant. But in your adjusted analysis, the result is more muted. You get a reduction of educational attainment by about three months fewer of education on average, plus or minus 9 months. So it's not statistically significant. So seeing that, your colleague says, just ignore the adjusted analysis and publish the unadjusted. So question, is that a good or bad idea? I think it's a terrible idea because socioeconomic status is an obvious, parent socioeconomic status is an obvious confounder in this setting. So just because why do you think it muted the result? Well, because, so the effect estimate changed, right? The effect estimate changed because you're reducing the bias. This is probably biased. This is probably a little bit less biased. There's also a little bit of random error, right? And this random error seems to have increased. So maybe the truth is actually, still a year, right? That if it's a year, minus 1 year, that still would be within the kind of random error that you're seeing here. So maybe that is the truth. But why is it that this variance is increasing? Well, because this SES, SES may be functioning a little bit more like an instrument and less like an explainer, right? So maybe what's happening is that SES is somewhere over here. It's definitely a confounder, somewhere in between this I and the X, because it's definitely still affecting this pretty strongly, but maybe it's more on this side of things, where it's primarily affecting the adverse childhood experience in a way that is greater than the way that it's affecting the outcome. That's a theory. Okay, so assuming you already adjusted for SES, what do you think would be the impact of unbiased invariance if you also adjusted for eye color? So eye color is definitely something that is here, right? It happens before the adverse childhood experience. It happens before years of educational attainment. So in theory, it's possibly a confounder. But most likely, it has very little to do with both the exposure and the outcome. Especially if, you could, if you want to stretch things, you can say, well, eye color is very correlated with race, and because of structural racism, then certainly there's going to be an association between eye color and educational attainment, and also between eye color and adverse childhood experiences. That's completely true. But if you're already adjusting for socioeconomic status and maybe race as well, then you're not, the eye color is not going to have an effect above and beyond those things. So you've already kind of broken those links. And so eye color ends up being a very, very theoretically possibly a confounder, but most like if it is a confounder, it's extremely weak. So the arrows, if you were going to draw like X as eye color, the arrows coming into these things would be very, 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 very thin, very, very thin dotted lines, which means that including it is not going to reduce the bias substantially. It's also not likely to have much effect on the variance either way. So including this thing will probably do basically nothing. Last one, should you adjust for high school grades? what did I say up here? Well, I said that here we're measuring, well, it's not written, but I said it that this is, let's say, measured in elementary school. So if that's the case, you should definitely not adjust for high school grades, because high school grades is something that happened after the exposure. So it's probably a mediator. And that is going to severely bias your answer. But it depends on how you define adverse childhood experiences. This is another case where, thinking very clearly about what the question is helpful, because if you say adverse childhood experiences at any time, then some people may have had one in high school, some people may have had one in middle school. So for some people, the high school grade would be kind of okay, but for some people it wouldn't be. And so it would really help to define an index time of saying, like, okay, in their year in 8th grade or something, did somebody have an adverse childhood event or not? And therefore, anything that is before 8th grade is fine for everyone. So index time would be a very helpful idea in this case. All right. More practice. Let's say you're interested in the extent to which harsh versus lenient sentencing in criminal cases for nonviolent offenders affects post-trial recidivism. So whether somebody ends up in the justice system again. And you have a couple variables that you're thinking about adjusting for. And here we just want to say, are they more likely to be an instrument or explainer? First one is, who is presiding over each trial? So I think that, and your mileage may vary, you should talk to people who are actually experts about this, but my intuition is that who you get as the judge, certain judges are more harsh and others are more lenient. So that's definitely going to affect the sentencing, right? It's up to them. But is that going to affect above and beyond what sentence you get? Do you think that will affect your recidivism? Like, is it plausible that, I don't know, maybe like somebody's sitting in the courtroom and the judge is just so harsh or so rude, or maybe it's so encouraging in some way, personally, that really affects how much somebody is willing to commit another crime, outside of how long the sentence is. Maybe it's possible, but it seems implausible, right? Especially because the interaction with that person is probably very short. These are nonviolent offenses, so it's, the trial is probably like a day or 2 days or something like that. There's not a lot of interaction. So really, this is something that is primarily affecting the sentencing and not directly affecting the outcome, recidivism. So the judge presiding over the trial is much more likely to be an instrument than an explainer. All right, so other factors. Pre-trial employment. So whether or not somebody had a job, will that affect the sentencing that they get? It's possible, right? Some judges will look at that and say, okay, this person is, working in the community and is somehow a benefit to society. Even if they committed a crime, I don't want to give them a harsh sentence because of the negative impacts to society. So, okay, it's possible. It's possible that could have an impact on the sentencing. But again, I think it's much more likely that it has a larger impact on the on recidivism, because if somebody had a job before, they're more likely to have a job after, and therefore perhaps less likely to commit a property crime or things like that. I don't know. Again, I'm not an expert. I'm totally making it up. There's all sorts of complexities here. I'm just kind of trying to give you again, as a biostatistician, your job is to kind of help people think about these questions. As a public health expert, your job is to be able to answer these questions and be able to understand why we're asking them, right? So when I give these kinds of answers, it's all made up, right? Because I'm a biostatistician. So this one I would say probably a little bit more like an explainer. Okay, last one is defendant's race, likely to be more of an instrument or an explainer. I feel like this one is kind of in between, right? It's a really important confounder. It's probably going to affect both pretty severely. We know that there's a lot of racism in the justice system, and there's also just strong associations in terms of recidivism with race as well, because again of structural racism and patterns of employment. So this is probably going to strongly affect both of these things. and therefore you would want to consider it as a strong confounder rather than as more as an instrument or an explainer. So if I were doing an analysis here and I wanted to condition on things or include certain things in my regression, I would definitely consider adjust for these two. This one, again, I would really have to talk to people and say, do I think that, is it plausible that the judge is impacting the post-trial recidivism in any substantial way? And if it's not, probably exclude it, because I know this will have a strong impact on the sentencing, and therefore this is a very strong instrument, near instrument. So I would definitely consider not adjusting for this one. Something you don't want to do, which is highlighted here in this problem, never compare results between different models and then selectively publish, right? So here you could say, oh, I did the adjusted analysis. I like the unadjusted analysis better because it gave me a better p-value, so I'm going to publish that one. Don't do it. Because you know that the model selection should not be based on any statistical consideration. It has to be based on domain considerations. At least, again, when I'm talking about what variables should be in, what variables should be out. When we start talking about nonlinearities and interaction terms and things like that, that can be automated with machine learning stuff. And we'll talk more about that later. But at least in picking what variables should be in and out, you can't just compare between different models and then go and publish one because of model selection bias, right? So the summary for this whole section is that model selection, it's complicated, and why you're doing it and what you should do varies depending on what the kind of question is that you're asking. So if you're doing pure description, it's very ad hoc because different models have different descriptive interpretations to begin with, and on top of that, you have to deal with the process of selection ruining the inference, creating bias and changing what the real standard error is. When you can sample split, but does it really matter because you don't even have a clear question? So for predictive models, it's very simple because you don't care about the coefficients, you don't care about anything. Just is the prediction error good or bad? And the only subtlety is, okay, you can't use the training error really because that's biased downwards, so you have to use a test error. Or, if you have small data, consider AIC, something like that. And now for causal models, we're just talking about the variable selection problem here. And for causal models, you have to do this on the basis of domain knowledge. There's no testing that you can do. It's not about statistics. It's about understanding what's a confounder and what's not and adjusting for the confounders. And the idea is you want to include those confounders, especially the strong confounders. Maybe omit instruments if you're very sure about them. And you want to definitely omit colliders. And the easiest way to do all of this is to focus on stuff that happened before the treatment and to make your question clear enough that you have an obvious index time and a well-defined intervention and a well-defined comparator intervention, or kind of like placebo intervention. So that's it for this time. Next week, we're going to get into logistic regression, and we're going to basically do all of logistic regression in 1 week because we will see that it completely mirrors everything that we did for linear regression. Because in this question-based approach, the choice of model, linear or logistic, is almost like a little bit of a convenience. It's not like, oh, the data determines what you should be doing. It's like the question determines what you should be doing. And so in this question-based approach, everything is very similar. So that should go very quickly and should be almost kind of review to a greater extent. There's a little bit of complication, but we'll get into that next time. All right, see you then.